and my name is Bhavik Bakshi. And let me start thanking all of you for joining and for the invitation to visit. And I am visiting, of course, virtually. And we are living in interesting times. What I'm going to do is give a little bit of an introduction just to myself, and then get into the presentation. And if you have questions or any comments along the way, you're welcome to send a chat message, although I may not be able to see them right when you send them. But I'll maybe pause at some point and take a look at them, or just wait until the end when there should be about 10 to 15 minutes at least for questions and any further discussion. So I'm hoping that technically this is working fine, and if there are issues, please interrupt and let me know, either by voice or chat. Voice would be more effective. Okay, so I'm a professor of chemical and biomolecular engineering at Ohio University. I've been here about 25 years. And for the last 20 years, I've been focusing my work on the challenges of sustainable development. How can we meet them from the engineering perspective? I got my degrees before that from MIT and the Institute of Chemical Technology in Mumbai. And other stuff, if you need to know, you can find it online or contact me. But I think that's enough for an introduction. So what I'm going to do is talk about, try to answer this question, or really, foster some food for thought and maybe additional research and inspire more work on technologies for sustainable development. If we really want to develop technologies and do engineering for sustainable development, which I'm sure all of us do, how can we deliver that? What are the challenges and what are some of the efforts that are ongoing to try and address this big and very important and urgent challenge? So I don't need to convince you that human well-being has seen tremendous improvement over the last few decades and centuries, in fact. A couple of indications of that are this left panel showing a reduction in poverty between 1990 and 2010. And this has happened across the world, and this is only focusing on the developing countries. And the right-hand panel is a whole bunch of lines that show the trend of the Human Development Index between 1990 and 2018. It shows all the countries for which this is reported. And in general, the trend is upwards. In other words, this is a metric of our well-being, and that has been improving across the world and over time. You do see occasionally some places like this particular line, it has gone down. This line represents Syria, and it has gone down because of the war and the civil strife that is happening over there. And you will see those kinds of decreases sometimes. But in general, our well-being has improved tremendously. As a species, we are doing exceptionally well. Despite the social isolation that we are practicing right now, 7.6 billion of us on the planet is also an indication of our success as a species. Engineering also, needless to say, has played a critical role in enabling this nice situation for humanity on planet Earth. I also don't need to tell you much about the ecological degradation that the planet has been experiencing and continues to experience, and the fact that our well-being really depends on goods and services that we get from nature, ranging from the water, the oxygen, the resources, and so on. So services that we get from nature, what are often referred to as ecosystem services, have been estimated to be worth trillions of dollars. And various studies have found that out of the 23 ecosystem services that have been identified by ecologists, 16 are degraded or highly degraded. And this cartoon on the right basically, I think captures the situation. On the one hand, we have been doing very well, but we are, potentially using up the resources that are the foundation of our well-being, which is potentially an unsustainable situation. So to give a few examples of this ecological degradation, I have several slides. I'm going to go through them relatively quickly. This slide shows the water stress in 2040, and it's an optimistic scenario where the effects of climate change are actually minimal. And as you can see, most parts of the world are likely to face water stress, including England, where you are, is going to be a highly stressed region as far as water is concerned. If we think about water quality, there are already challenges associated with the pollution due to plastics in the ocean. There are big plastic islands in various places in the ocean, as indicated on this map on the right. And this picture on the left is taken in Hawaii, where you can see plastic litter on the beach over there. So in this case, the plastics are exceeding nature's capacity to regulate water quality. Many other examples of exceeding nature's capacity to regulate water quality include the creation of harmful algal blooms, and there are such sites across the world on coasts, including that of many countries in Europe. Another ecosystem service that we get is that of disease regulation. And this is particularly relevant today in the presence of this COVID-19 pandemic. Nature has the ability to regulate pests and diseases, but biodiversity is essential for this ecosystem service to work properly and to be available. As is shown on the right over here on this slide, it is suspected that the COVID-19 outbreak is a zoonotic disease, and it has jumped from animals into people, as is shown in this bottom panel. And then there have been local outbreaks. Wuhan is the city where the outbreak seems to have first occurred. And it managed to jump and travel across the planet thanks to our exceptionally good networks, almost too good now. And that has resulted in this huge pandemic, and the fact that I'm not present over there in person, which I would have loved to meet all of you in person, but maybe that will be at some other time. So this is another very important ecosystem service that our well-being depends on, and that has been highly disrupted. But this pandemic is actually nothing as compared to a potential future challenge that we are going to face. We are already facing the challenge now, but it's only likely to get worse, which is the degradation of the climate regulation ecosystem service that nature provides. And this graph over here shows the trend of carbon dioxide concentration in the Earth's atmosphere, estimated and measured over the last 800,000 years. And we, as of 2 days ago, April 27th, we were at 416 parts per million. This is as measured on Mauna Loa in Hawaii. And before the Industrial Revolution, we were at around 270 parts per million. Despite the economic slowdown and the reduction in travel and manufacturing, etc., according to these measurements, our CO2 concentration in the atmosphere still hasn't really shown any significant trend. I expect we will see it in maybe a few days or weeks, but at least as of today's data, nothing can be observed. So, in response to these sorts of challenges, these environmental challenges, there is a lot of work going on in academia. And this graph over here shows the increase in the number of publications with the word sustainable or sustainability. That's the orange bar. It's an exponential increase, as you can see. If you add engineering to it, that's the blue bars, and that's also increasing exponentially. Nearly 7,000 papers have been published in 2017 that have at least these keywords included in them. Within the domain of process systems engineering, which is sort of my parent discipline, my background, you look at process control, process design, product design, and metrics. Even there is an increase. There has been a significant increase over time in research that has sustainability and sustainable development types of challenges being considered. What has also happened is that over time, process systems engineering, started out looking at equipment and then gradually looking at processes and process design, to looking at enterprises, supply chains, and in the last 10 to 15 years, the boundary of process systems engineering has expanded to consider the life cycle of various products and processes that we make. So, and that expansion has happened, in response to these environmental challenges that I mentioned. Industry also has been responding, and this kind of busy slide here, picture here is, the thing to focus on are the green bars, which indicate the number of, the percentage of organizations that respond positively to this question. Does your organization have a sustainability strategy? The chemicals industry noticed more than 80% of global organizations are responding positively to this. And the trend has been that of increasing this over time. So corporations are also very much, into trying to respond to these environmental challenges that we face. Of course, one of the outcomes of that has been new technology. And this graph over here shows the dramatic reduction in the cost of renewable energy. And if we focus on the yellow part over here in the middle, 0.36 was the cost of solar photovoltaic energy in US dollars per kilowatt hour in 2010. And that has gone down in 2017 to about 10 cents per kilowatt hour. This green bar indicates the region of costs of conventional energy, fossil energy. So solar photovoltaics is now competitive with conventional energy, as you probably know already. So this is a tremendous improvement, tremendous advance, and there is increasing adoption of solar energy, and that is expected by many to be a huge part of the solution to many of the challenges that we face. So the question, nevertheless, is, will technological advances address the environmental challenges that we are facing? And to try and answer that question, I think it is useful to just look at the history of technology. And turns out it has been a history of intended and unintended effects. Starting with the horseless buggy or the car. One of the intentions was to eliminate horse manure from the urban streets. But it did eliminate that, but the unintended harm was smog and climate change. Artificial fertilizers intended to enhance food production, which they did, but they also gave us harmful algal blooms, and so on. Chlorofluorocarbons were really good refrigerants, but they gave us the ozone hole. Plastics, very convenient packaging, but there is ocean pollution, and so on. So the question that is, I think, very relevant to all of engineering is, will today's so-called sustainable technologies also cause unintended harm, as has happened in the past? Obviously, we don't want that. So the real question is, how do we make sure that that kind of unintended harm does not happen? So it's important, I think, to understand the nature of environmental problems and the fact that environmental problems tend to shift in space and time. The local problems due to horse manure basically got replaced by problems that were over a larger space and time, such as smog and eventually climate change. Environmental problems also shift between flows. You may reduce energy consumption, but it may require more water. And they tend to shift across disciplines. You may have a more efficient technology, but it encourages consumption, and due to behavior and economics, demand and environmental impact goes up. It's also critical that sustainability means that we stay within nature's capacity. We need to know what nature's capacity is and develop things that will make sure that we respect that capacity. So can engineering solve these kinds of problems, right? Those are some of the questions and challenges that we are facing. Going back to, history again, and if we think about the foundations of engineering, most of the foundations that we rely on today, the laws of thermodynamics, over here, I have Boyle over here with ideal gas law, and Carnot and Boltzmann and Gibbs and all these other stalwarts. A lot of the work that they did has formed the basis of the technology and the science that we do today. At that time, where all this was developed roughly, more than 100 years ago, around 1900 or before 1900, population was less than 2 billion people on the planet. GDP was, a little bit over $1,000 per person. At that time, the world was relatively empty. The human footprint was small and nature was vast and seemed infinite. So the principles, the foundations of science and engineering that were developed at that time ended up taking nature for granted. We implicitly assume infinite sources and sinks even today. And we do not take into account nature's limits. We may design a process to make it efficient and use maybe minimum water, have minimum greenhouse gas emissions, but we do not consider whether the watershed has the ability to provide the water that we are demanding and whether the atmosphere has the capacity to take up additional greenhouse gases that we maybe emit. So, the other thing that happened is disciplinary specialization. Various disciplines diverged. And the benefit was that we could then ignore complex interactions. And the focus of engineering has become on developing more efficient technology, just as on economics has become that of ensuring economic efficiency. But more efficient technology often has resulted in shifting of impacts outside the system boundary and the unintended harm that I talked about earlier. So these are some of the characteristics that are very inherent in the paradigm of engineering that we use today that have, a historical reason. If you think about today's world, it's very different from the world that it was when this basic paradigm and the foundations were developed. Our population, has quadrupled to about 8 billion people, 7.6 as of last count. And our GDP has also gone up by about 6 times to about $8,000 per person. To the extent that from the 1950s, geologists consider the beginning of a new geological epoch that they're calling the Anthropocene. There are also indications of the CO2 concentration in the ocean having gone up and the pH in the oceans decreasing, global temperatures going up, and CO2 concentrations, as I already mentioned, also increasing. So what we need is to do an engineering for a world that is full now. It is not empty anymore, the way it was when the foundations were developed. The human footprint is huge now, and ecosystems and its services are scarce and becoming scarcer. So it seems to me that the current paradigm of engineering that we have been following for many decades, a couple of centuries at least, will continue causing unintended harm. It will not result in sustainable development. So what is needed is for this paradigm to shift, for it to adapt to a full world. And Einstein is credited with the statement, which is very relevant over here, as in many other situations. So he said, apparently, the significant problems we face cannot be solved at the same level of thinking we were at when we created them. So we need to move to a new level that is, beyond the level at which we were when a lot of these challenges associated with the unintended harm were created. So with that background, the work that we've been doing in my group, for the last many years, are focusing on 2 broad areas. One is to develop methods that avoid burden shifting, the shifting of problems across disciplines and across time and space and so on. And we're also focusing on trying to learn from and respect ecological systems, from nature. Many different areas of work over there, and I'm not going to obviously cover all of them, but just to give you a broad overview, we've done work related to life cycle assessment, developed methods that will incorporate the role of ecosystems and ecosystem services, including ecological carrying capacity in life cycle assessment, applications to a variety of products, including biofuels, agricultural products, etc. Many things related to design of various types of systems, obviously, things relevant to chemical engineering, but also urban systems and agricultural landscapes. And we are currently working on ways of coming up with a climate action plan for our campus. And I'll talk a little bit about these ideas of eco-mimicry and efforts towards a circular economy. We have developed this framework that I'll tell you more about that we're calling techno-ecological synergy. And the other area that we are also focusing on is, to account for the economy, the markets and human behavior and their effect on engineering decisions. Today, in the interest of time, I'm mainly going to focus on this first box over here and not really spend much time on the economic aspects. I'll just give you a glimpse. I'm happy to answer questions later on if you're interested. And there are several published articles out there also. So let me first start with this concept of a circular economy, just to explain it first, and then get into some of the research. So linear economy is the kind of system that we have traditionally been following since the Industrial Revolution, where, as shown on this slide, we extract resources, we manufacture products from them, distribute the products, use the products, and then dispose the products. This kind of a linear system is not very efficient. It tends to have large environmental impact. And, a lot of people for a long time, many decades, have been envisioning and arguing in favor of a circular economy because it would mimic nature. Nature cycles are closed. So circular economy would take some resources, but a small quantity from nature. It would go into manufacturing, distribution, use. No, notice there is no disposal in the circular economy. Everything gets reused, repaired, or remanufactured, or it goes back into the manufacturing stage, or it gets recycled. To enable this circularity, what is needed is innovation. We need smart engineers and some creative ideas to enable a circular economy. So, what we have been focusing on specifically is the circular economy for plastics. And the diagram that kind of represents some of the characteristics of that is shown on this slide. So, obviously we have manufacturing that uses resources from the outside of the circular system. We make the products, consumers will use it. So consumer and household behavior matters. The waste gets collected and goes to a material recovery facility. And then there are various ways of recycling, chemical recycling and mechanical recycling and so on. And some of these will go directly back into the manufacturing steps, similar to the previous, the circular diagram on the previous slide. Or some things may go to other economic sectors and other parts of the supply chain. At each stage, there are these arrows that are shown over here, which indicates leakage to the environment. This leakage could be littering of the plastic products, or it could be, and other emissions to the environment of greenhouse gases and volatile organics, etc. So, at each step, you can imagine there are lots of alternatives. For example, our focus has been on plastic grocery bags, and I'll show you some results of that in a little while. So there are many different kinds of grocery bags that are available, made from polyethylene, polylactic acid, polypropylene, and so on. Many different ways of manufacturing them, many different types of raw materials that we can use. We could use biomass to make ethylene and then ethanol, or we could go to a fossil route. So each step has lots of alternatives. And each combination of alternatives, or each pathway towards a circular economy, has different degrees of circularity and different environmental impact, or different life cycle environmental impact, and a different cost. So the question that we are interested in is, trying to figure out, so how do we determine what is the quote unquote best pathway that meets these goals of circularity, life cycle environmental impact, and cost. And eventually what we want to do is to use this and develop a framework that allows us to encourage innovation and help us discover and innovate new pathways and new products and new ways of meeting these objectives that I've mentioned over here. So before I go into any methodological part, just to make sure that people know what life cycle assessment is, this is just a very quick introduction to that. The idea is to consider, if we have a product, in this case it's a paper bag, we want to consider the entire life cycle, all the way starting with extraction of resources, the manufacturing, transportation, use, and then end of life, goes to a landfill, gets recycled, reused, whatever. So, this is an approach that has been around for a while. And for our work, we rely on life cycle inventory databases for the common processes. But a lot of the end of life processes, the data for that is not available in many of these life cycle inventory databases. So for that, we are relying on the literature for waste management, and also on surveys to get information about household behavior. The conventional LCA framework is not directly usable for considering sustainable circularity. So that is something that we have modified and developed a different theoretical framework. I'm not going to get into details of that right now, but I'm just going to show you how we use the framework and some of the results from that. So to design for sustainable circularity, we end up solving a multi-objective optimization problem that is summarized on this slide. So there are 3 objectives that we are considering: degree of circularity, the life cycle environmental impact. Specifically in the case study, we are focused on global warming potential, and to minimize cost. Okay. The circularity index is defined over here. It's a ratio of the different, we take into account the whether we are upcycling or downcycling, the quality of the resource that is being recycled. Are we incinerating and just getting heat, or are we actually recycling the product? That is taken into account with the help of a quality indicator. That could be cost. We are also looking at the use of thermodynamic metrics based on exergy for this purpose. This equation here is based on the framework for representing the life cycle network of alternatives, effectively the superstructure of all the alternatives that are available, in this circular system. We also need to satisfy certain household requirements for grocery sacks, and there are also nonlinear process models that may come in if we have that available for some of the manufacturing and other steps in the system. The type of results we are getting are summarized over here. So this is a 3-dimensional Pareto surface essentially. So we have the degree of circularity, the global warming potential, and in this case, the life cycle cost. So you can see that this point here has the lowest cost and the lowest global warming potential. It also has the lowest circularity. So what does that result look like? What we find is that in this result, it is best to use low density polyethylene bags. They get used in the household, and the households just litter everything. Everything gets thrown into the environment. No recycling, no circularity at all. So circularity index is 0. That's why there is a red here, because this is really bad from a circularity point of view, but it's really good from a cost and global warming potential point of view. An intermediate result where they are all kind of, all the metrics are sort of, similar. We find that using polylactic acid bags is better, and some LDPE bags, but there is still a large loss. Circularity is still relatively low. Highest circularity gives you highest cost and highest global warming potential, and there it makes sense to use polylactic acid bags. Notice that the circularity still goes to about 65%. So 35% of the bags are still getting lost. So this is what we can do with the bags that are available in the market today. Obviously, there is plenty of room for innovation, and there is a lot of work going on to improve the situation. So, after giving you that glimpse about eco-mimicry through circular economy, let me spend the rest of the time focusing on this issue of how do we account for the role of ecosystems in technology development and in engineering design. So again, quickly to remind you, engineering does depend very much on ecosystems. We get all of our goods like water, minerals, biomass, etc. from nature. It's also the sink for our wastes. And we get lots of services that I mentioned earlier: air and water quality regulation, food and water provisioning, etc. And this figure here is just essentially summarizing that. Vegetation can take up all sorts of pollutants and provide biomass and other benefits. And wetlands can clean water and provide lots of benefits. So we have been working on developing this framework that we are calling techno-ecological synergy. And traditionally, our focus, in engineering has been on improving the efficiency of technological systems and of the life cycle of these systems. Increasingly, we've been focusing on that. And we are also looking at circular economy, a lot of work going on in that area, and industrial symbiosis, byproduct synergy. These are some of the efforts that are already out there. And I described some work on circular economy earlier. The thing that is missing from all of these directions of work is the accounting of the role of nature. I mentioned ecosystems, they are critical. Without that, we cannot sustain any of our activities. And engineering traditionally has ignored them. So what we are trying to do is to include the role of ecosystems and try and understand how can ecosystems actually utilize some of the wastes that may be generated from human activity, and what are the resources that it could supply to human activities. And eventually, what we would like to be able to do is to go to a system that is fully closed loop, truly synergistic between technological and ecological systems, or between human and natural systems in a broader sense. So, to explore whether this idea makes any sense, we have been studying this particular biodiesel manufacturing site that is, near Cincinnati in Ohio. And here is the biodiesel manufacturing site, and here is some land that is available for the company. And what we have considered is the use of a treatment wetland for treating the water from this site, and the use of vegetation for treating the air emissions that are coming from this site. This site we have assumed has a small combined heat and power plant that is burning coal to generate the electricity needed for this biodiesel manufacturing process. And we have solved this problem in two different ways. Oh, sorry, one thing I should say, so essentially what we are doing over here is including nature, including ecosystems as if they were unit operations in the design of a chemical process. So if you look at this flow sheet, we have the usual unit operations, but now we are also including a wetland and local vegetation as if they were just unit operations, and trying to do an integrated design, with all of these things in together. So wetlands, as it turns out, have been used in industry. There are many places that do use wetlands for treating water, but most of the times they are introduced as end of pipe. So the chemical process is designed first by maximizing profit subject to various constraints, and then the ecosystem is added on it as end of pipe treatment. So I'll show you some results for this type of an approach. And I'll also show you results if we were to do an integrated design of the technological and ecological system together. So we will have two objectives here: maximizing profit and minimizing impact. In fact, the net supply of water is what we will focus on. There are various constraints, technological constraints, and also the ecological constraints are included in there. So the results we get are summarized on the next 3 slides. We are maximizing the net present value. That's our economic objective. And we are maximizing the net water supply. Notice that the water supply over here is negative, meaning that we are withdrawing water from the environment. That's why it is negative. If the value was 0, then it is neutral. Whatever we are withdrawing, we are also providing back to the environment. This is the Pareto curve for an end of pipe design with a technological option, which is an anaerobic baffled reactor. This is the region where we can get feasible designs, on this side of the Pareto curve, and on the other side, they are not reachable. But if we can go to the other side, there are potentially win-win solutions and innovative designs that exist on the other side. If we were to, instead of the technology, we were to use a wetland, we can already get a design that is on the other side of the Pareto curve with a technological solution. But this is end of pipe design. If we do integrated design, we can do even better, as is indicated by these two Pareto curves over here. We are moving on to this other side of innovative solutions. But if we were to recycle the water from these facilities, which is possible, it takes a little bit more money, but that kind of a design is certainly possible. In that case, we get these Pareto curves on the top part. Okay, and notice that if we use a wetland that is integrated and the water is recycled, we can get close to net zero water at the site. And if you look at this point, for the net present value, it is not that much more expensive than a conventional approach. So what this indicates, and we've done other examples of this type, that there are opportunities potentially for including ecosystems in engineering design, just like any other technology, and we may be able to develop win-win solutions. We've also included vegetation, to take up air emissions, and that can give us further improvement in the results. So basically, this and many other studies that I will summarize a little bit later is indicating to us that there is some promise to actually including ecosystems in the type of engineering design that we tend to do, something that we have traditionally ignored or taken for granted and have been wanting to dominate. We've done studies that also look at the entire US, and I'm going to skip a couple of slides over here in the interest of time. But we have looked at, the entire country of the United States, 3,000 plus counties, and we have found, that in these blue counties, there is enough vegetation to take up all of the SO2 emissions. In these orange counties, only 0 to 25% of the emissions can be taken up. We have looked at scenarios where we can restore vegetation and see how much improvement there can be in that. From a tech engineering point of view, the more interesting thing may be that we have identified, which sectors of the economy does it make sense to rely on ecosystems rather than technologies for mitigating emissions. So a lot of the sectors, such as agriculture, power generation, mining, oil and gas, it makes sense. Ecosystems are actually cheaper. But for other sectors such as industrial boilers and many manufacturing processes and metals processing, it actually is found that technologies may be less expensive. So this also allows us to sort of look at things at a larger scale, looking at the broader economy and the potential value that accounting for ecosystems can provide. So as I said, we have applied, done lots of different examples. Many of them are listed over here. And in all cases, what we have found that there are opportunities for finding win-win solutions, moving the Pareto curve to this other side and creating this additional design space that becomes available due to the inclusion of ecosystems in our design, due to techno-ecological synergy. So, if there are so many cases where this looks attractive, one thing that you're probably wondering is, how come people are not using this kind of an approach? How come for the last 200 years, in engineering at least, we have just ignored nature and not really discovered these types of opportunities? I think there are many reasons for that. Some of them are summarized over here. There are several barriers. In technology, we desire predictability and control. We turn on a light switch, we want the light right away. Nature is not like that. I don't know if it is cloudy over there or not, but over here in Columbus, it is certainly cloudy. It's going to rain today, no sun. Nature tends to be unpredictable, intermittent, and slow. There are many benefits of ecosystems. They go to society. They do not necessarily improve the corporate profitability, partly because our economic system takes nature to be free. Also, current environmental policies do not allow any credit for ecosystems. Very importantly, engineers, surveys have shown, are among the least ecologically literate people. We know very little about nature. We don't study anything about ecology in most curricula. So we don't even think about nature. Nature is something that we want to dominate. And as a result, we many times end up over-engineering the solutions. And it looks like from our work and other work also, that there may be ways of maybe doing less engineering and doing more synergy with nature. And that may give us a better solution from a sustainability, resilience, and profitability point of view also. So we have been trying to address this intermittency issue, and I want to show you some results that we have obtained for that so far before winding up. So for this work, which is ongoing right now, we have preliminary results. We are considering a chloralkali process that is in Galveston, Texas. That's where a lot of the chemical plants are located. And our problem includes various decisions. We are trying to plant trees to mitigate the NOx emissions because there is a big problem with ground level ozone formation in that region. And we are looking at using a selective catalytic reduction unit as the technological solution versus trees as the ecological solution. We want to have a certain production rate of chlorine. And we are trying to decide, what fraction of the emission should be treated with technology versus ecosystems, and how should that change over time, while taking into account the variability in the capacity of the vegetation to take up NOx emissions. There is variability during the day. There is variability with respect to seasons. We are using a couple of big ecological models over here. One is the Forest Vegetation Simulator, and the other one is called iTree. They are both developed and available from the US Forest Service. So one slide summarizing some of the results. This is over 20 years. The time period, the x-axis is over 20 years. And what we are finding over here, this is showing the fraction of technology use. We start out, there are hardly any trees, so we don't really can rely on trees. but we start planting trees from year 0. We rely a lot more on technology, but you see over time, we rely on less and less on technology. But you see there is this oscillation that appears. In the winter, we do rely more on technology and less on ecosystems because the trees have less leaves. This is the production rate. We're allowing the production rate of chlorine to vary. And even there, you will see that there is less production in the winter and more in the summer. So, basically, this solution ends up costing $18.4 million as compared to $18.9 million, which is the conventional technology only solution. We do need a land area of 32 square kilometers, in this case. Of course, land is needed. Ecosystems, do need land. But what it shows us is that there may be ways, if the engineering is willing to adapt to the cycles of nature, then there may be ways of actually building synergies between technological and ecological systems and getting, economic benefits. And this is just conventional economic analysis. But nature provides lots of benefits to society also. So we have done an additional analysis where we compare the private cost and the public cost. Private cost is basically cost to company. This is just conventional profit. So if you were to use just technology, this x-axis here is cost to society, and this is cost to company. Cost to society includes things like the cost due to the emissions, the health impacts of NOx emissions, for example. The lost wages due to illness, due to less recreational opportunities, things like that. All of those are included in this cost to society. Private cost is just conventional profit. So you can see there is a trade-off over here. If you want high cost to society, it looks like the cost to company, the profit is going to be lower. On the other hand, if you want high profit, I'm saying it the other way around. If you want low cost to company, high profit, the cost to society is large. If you want to reduce the cost to society, the cost to company keeps increasing, and you end up, at a point where if you want cost to society to be 0, then the cost to company is quite high. So this is basically the Pareto curve showing the trade-off between the cost to society and the cost to company, the public cost and the private cost. And this is using only technology. This is conventional design, conventional engineering. If we were to use a TES approach, okay, the one that I showed you on the previous slide, for that case study, this is the Pareto curve that we find. It turns out that by incorporating vegetation over a 20-year period, it is possible for the cost to society to go to 0, and the cost to company is only $10 million per year, whereas the technological approach gives a cost to company of more than $20 million. So there is a potential large benefit to society from the use of a TES type of an approach. If you had more ecosystems than this 0 cost, then the additional ecosystems will actually provide a net benefit to society. That is essentially something that a lot of corporations are striving for, net positive impact manufacturing. And that is what could be done if we had, a greater synergy between these human and natural systems. Okay, so let me conclude over here. What I've tried to convey to you is that technology obviously is essential for human well-being. We must continue all the work that we are doing in developing it, but we must also keep in mind that it has contributed and continues to contribute to ecological degradation, including the current pandemic that we are all experiencing. The paradigm of engineering was developed when the world was relatively empty. It needs to be modified. It needs to adapt to a full world. What we need, it seems to me, is a sustainable engineering that accounts for the role of ecosystems and the interaction with society. And I've only described a couple of things that we have been working on. One is this idea of eco-mimicry or circular economy. How do we design a sustainable and circular economy of various products? And the work that we are doing on eco-synergy or techno-ecological synergy. How do we develop these integrated networks of technological and ecological systems? There are lots of challenges and opportunities for future work across disciplines. So to summarize then, will engineering deliver? And what are the opportunities? What is the real need for further work in the future? As you know, engineering science, if you like, has tended to focus on the small scales. It tends to be reductionist oriented. But there's a lot of work at the molecular and atomic level, going all the way to equipment and a little bit towards processes and so on. Process systems engineering really goes from the equipment scale, and as I said earlier, it is connecting increasingly with the life cycle scale. There is also work in the discipline that has been called industrial ecology that has been focusing mainly from the life cycle scale, trying to connect with the economy. What is really needed is to connect, cover all of these things. That's what sustainable engineering is attempting to do. And ecosystems also need to be considered over here. So at each level, at each scale, there is an interaction with nature that also needs to be taken into account. There are potentially opportunities for synergies, for developing systems that are better from a sustainability, resilience, and cost point of view, and to understand the trade-offs. It's not always going to be win-win. To enable something like this, conventional engineering is certainly not going to be enough. It seems to me what is needed is a deep convergence of engineering with ecology, economics, and sociology. This is a huge challenge. We diverged 200 years ago. All these disciplines diverged. It is time to start, bringing some of the elements of these disciplines together through deeper convergence. What that could lead to is a vision that is like this, and I'm not going to talk about this or show this right now, but just want to acknowledge several people who have contributed to this work, several graduate students, collaborators, across many disciplines and across the world, and support from various funding agencies. And I'll go back to this slide for you to just take a look at that, at what I think is really needed. What is the vision that we need to pursue to really make sure that engineering makes positive contributions to sustainability, and make sure that the next big pandemic that we face we don't really have to face it. We address the challenges of that in advance. Thank you very much. And I hope you were able to hear me and follow the work. And I'm happy to answer questions and take comments and any other input that you might have. So I see questions over here. So maybe what I can do is just go through the questions. And try to answer that. You're welcome to add questions to this, and I'll answer all the questions. If if we run out of time, I'm happy to stay on for further additional time as well. Okay, so the first question here is, what about nuclear energy? Well, nuclear energy, I think, is certainly part of the answer. It does have many benefits, particularly from a carbon neutrality point of view and things like that. But, there are challenges. I mean, eventually, it is not something that is going to be truly sustainable. There is unintended harm. There are unexpected side effects. We know those very well, the Fukushima disaster being among the more recent ones. But it does need to be part of the solution. All options need to be on the table, in my opinion. The GDP graph, does it take inflation into account? Yes, it does. That GDP graph is actually some really interesting work done by an economist, I believe, in Belgium, and he passed away a few years ago. But it is, he has collected data that goes all the way from, the 0 BC, essentially, I mean, and up to now. It does take inflation into account. So with inflation, yes, our GDP has gone up from about 1 or 1.5 in 1900 to about $8,000 per person, roughly now. Okay, next question. I was just wondering how is the leaks to the environment is considered in the multi-objective. Okay, yeah, the leak. So you're talking about the leakage of plastics to the environment in the multi-objective optimization. So what we did was we have data about the quantity of emissions, actually littering that is happening at each stage of the circular cycle. So let me go back to that slide quickly. Yeah, so this cycle, right? So these leakages that you can see, these arrows that you can see, we have data for that. So for example, a lot of the collection and logistics and segregation steps, there is some data available, some of it from the LCA literature, from the life cycle inventory, a lot of it from, specific or papers about specific technologies. For the consumer behavior part, we relied on a survey that has been done of consumer behavior and their use of plastic bags. And that also contained information about the littering that happens as a part of a typical household. So we do have data about littering and about the leakage that we are relying on. So hopefully that answers your question. If not, I'm happy to provide more details. But let me move on. What kind of challenges can you have when trying to develop and implement a technology ecological synergy solution? How competitive is it to standalone technology solution in terms of cost, development, and implementation? Can you please expatiate on this? Sure. So, I mean, there is no dearth of challenges. Most of the examples, most of the problems we have done tend to be of steady state systems. We've assumed static behavior. And our intention has been primarily to make sure that this idea is not stupid, to put it bluntly. When we first thought about this, we thought, well, we first need to make sure that this does make some sense. And the more we are looking into it, the more we are realizing that there is a lot of value addition that can be provided from this. There is no dearth of challenges, so as compared to a standalone technology solution, when is a ecological synergistic solution going to be better? Well, so for the air pollution study that we have done, what we are finding is that the reason across the United States, vegetation is able to provide a lot of air quality regulation ecosystem service is because the air is relatively clean. If the air was really dirty and we had a lot of acid rain and those kinds of problems, ecological solutions would actually not have worked very well, because the acid rain would have killed the ecosystems as they did, many decades ago, before the 80s primarily. So when emissions are at a high concentration, it seems that using technology makes more sense. Technology generally is cheaper and it is more sensible even from an environmental point of view when the emissions are at a high concentration. But when the emissions are at a lower concentration, as is the case with NOx and SOx and particulate matter in many parts of the world today, not all parts, but many parts, including parts of Europe, then ecosystems start becoming much more meaningful. They tend to be less expensive. It's a distributed solution. And they also bring all of these sustainability benefits. So there is a sweet spot when a TES system is going to make more sense. Okay, this is an open question. I don't know the answer to it, but the insight that we have so far is high concentrations prefer technology. Maybe ecosystems are not worth using there, but when your technology does its job up to a point, it is great. When you go to lower concentration, technology starts becoming very expensive. Ecosystems tend to be much better in that case. Slightly long answer to that. So let me move on. It seems like there are plenty of developing technologies out there to help us tackle environmental issues. How can we convince investors to get involved when the technologies have not yet been proven commercially? Yeah, that's a great question. It turns out that for ecological approaches, investors, it seems, are getting more and more convinced. I can give you a few examples. If you, let's start with the chemical industry. If you go to Dow Chemical's website and you look at their sustainability goals, one of their goals involves ecosystems and actually monetizing the value that ecosystem services provide. And they want to be net positive from that point of view. You go to Unilever, which is kind of in your backyard over there. Unilever is among the leaders in this type of an effort. Also, their website also talks about, their effort towards including ecosystem. But this is a lot of talk, right? What is needed is action. Most of the action that I'm seeing so far, and it is not a lot, I will agree, is in the urban design space. A lot of cities are putting in wetlands and bioswales and other sort of what they are calling green infrastructure. And we are finding it to be competitive, better than so-called gray infrastructure. A lot of this is, sometimes it seems almost ideological. There's not a lot of science that's going behind this, but a lot more work is needed. But that is one area where investment is being made and hopefully will continue. Okay, Moving on, for ecosystems included in the manufacturing design process, is it feasible to have indoor on-roof fish tank and basement type solutions in factories, wetlands? Yeah. For factories where a wetland may not be available. Yeah, I mean, I think solutions are needed at all scales, but the thing to do is not blindly assume that an ecological solution is necessarily going to be better, because it need not be, as I mentioned earlier. But I think, if we use our innovation and look at these types of options in the design, I think there are some unique approaches and designs that can be developed. I mean, in my opinion, work is needed at all scales, be it a fish tank in the basement to be it a 100 square kilometer forest that the region is relying on. Okay, moving on. Hydrogen technology, isn't it better than lithium ion technology in terms of sustainability and environmental friendly, given that the hydrogen is produced? What are the reasons that the major automakers are neglecting the potential of hydrogen cars? Hydrogen is tricky. The problem with hydrogen is that it is not directly available. You cannot mine for hydrogen. You have to produce it from something. If you get it from methane, from natural gas, then you're releasing carbon dioxide. And methane is obviously a fossil resource. So there is a depletion issue over there. If you get hydrogen from water, you need a lot of water, not a small quantity of water. We have done calculations for our region here, which is very water rich, but there is a substantial pressure on the watershed. Whether it is better than lithium ion or not, it kind of depends. I think if we apply a holistic approach and take into account, use some of the methods that I was talking about and that others have been using, and evaluate it, maybe then we can come up with the appropriate answer. It's important also to sort of make sure that we don't get locked into any technology. We need to have an adaptive management type of an approach. Maybe lithium ion makes sense now, but gradually we may realize, there may be advances in hydrogen and stuff like that. And maybe those, type of automobiles will become available later on. The other thing to think about, though, is from a mobility point of view, right? That's a bigger scale of thinking. And maybe we need to design cities that don't require us to use any of these types of automobiles at all. And that applies very much to many North American cities where, without a car, you basically can get nowhere. Okay, let's move on. I was wondering where you see the responsibility for paradigm shift, economy or politics in the US? Who can create more impact, greater call for change? Yeah, great question. I wish I knew the answer. I mean, what I can say is all of the above, right? The way I try to think about it is that as engineers, assuming that you are an engineer, whatever profession that you belong to, start from there. Start, from here and now. Ecosystems are really important. Go out, take a walk, look at the local birds and animals and plants and species and stuff like that. Become more familiar with them, become more ecologically literate, right? That's sort of the first place to start. I think this is something where, things need to happen at a grassroots level. Of course, they need to happen at the level of the economy. Politics also matters. I think if we all push and we show, I mean, these case studies that we are doing, we are trying to show that there is real value over here. And increasingly, we are starting now to have some interest from companies, for example. We have done small projects for Eastman Chemical, for Dow Chemical, for American Electric Power. They're little boutique kinds of projects. But, I think work is needed at all ends, from all walks of life, all professions. Who can create more impact? I don't know the answer to that. I think all of us, these are complex systems. There's probably a tipping point that we need to get to, and then change will be fast. Okay, 2 questions. All right. Try to consider uncertainties in the integrated ecosystem and process design. Okay, let me focus on that first. To some extent, yes, but there is more work needed. So let me go to this slide here where I did have some, yeah. So over here, you see these bars, right? These orange bars and these light green bars. They are not exactly uncertainty, they're representing variability, seasonal variability in our results. So we are working towards considering uncertainty. There is a lot more work that we need to do over there. So that is active research for one of or two of my graduate students right now. There are nice methods out there that are, I think, very relevant and could be adopted over here. Maybe there are opportunities here for also collaborating with people who have some of these methods and so on available. Okay. Okay, when it comes to optimization, can you elaborate more on how to deal with difficulties in solving, large size, multi-scale, nonlinear problems? Great question. These problems are hard. This example that I'm showing you, we are currently working on trying to solve this at an hourly scale over 20 years. And the reason we're doing it at an hourly scale is because we want to start looking at short-term real-time optimization kinds of integration now. And we are not able to solve that problem right now. Our optimization, basically, that just becomes too much. So we're looking at surrogate models and some of the other methods for trying to make that more efficient. But there are, big challenges over here. These are really, I think, difficult problems, but one thing at a time. We started with steady state. Then we went to this kind of a result, which is at a monthly scale. I think there are challenges and opportunities, at the level of design, planning, scheduling, real-time optimization, fault detection and diagnosis, and also process control. If we were to go to a feedback control mechanism, maybe use MPC, model predictive control, and those sorts of things, some of these challenges maybe could be dealt with. There are more questions here than answers at this point. So what we are doing, most of the work we have been doing is using GAMS. The results I showed you, obviously those problems we can solve, but there are others that we are currently not able to solve and are working on trying to come up with either linearized versions or surrogate models to try and make the problems more tractable. Okay, so let's see.
Bhavik, sorry to interrupt you. It's Sarah here. You missed one of the questions. Sorry, I know you've got quite a few. So the question is, could you please comment on how you handle the large amount of uncertainty or lack of information in quantifying ecosystem value services?
Right. Okay. All right. Yeah. Thank you. Thank you, Sarah.
Sorry about that.
No, that's perfectly fine. Sorry for missing that. Right. A large amount of uncertainty. So, I mean, the initial work we did, honestly, we did not consider uncertainty. Okay. This work that we are doing now with this chloralkali process, and we have another project that we are doing where we are considering a coal burning power plant and trying to develop this kind of a design for that. We are using information. So these ecological models do have uncertainty information, right? We are using iTree and this forest vegetation simulator. They do have some uncertainty information that is available in them. So we are trying to incorporate that in the solution of the optimization problem, using stochastic programming methods and so on. I mean, other than this result that I have here, and we have several versions of this. In fact, on this slide here, there are 3 scenarios that we have on this right-hand side that they're quite small. But in those things, we have taken some of the variability into account. The uncertainty in ecosystems, is something that we are, that requires good collaboration with ecologists, which fortunately we have for at least some of the models, and they need to be able to provide us with the uncertainty information. But it's a work in progress. There are, lots of challenges. Some of this information is not easy to get a hold of. Many times it is not even available. So, that's kind of a partial answer to that question. Okay, so. I know we are over time, but as I said, I'm happy to continue on. I don't have any other things scheduled at this point, and you are all also probably sitting at home, so hopefully you can also stick around if you like. So let me see, where was I?
Sorry to interrupt again. Just the question from Nilay Shah that starts to what extent. And also thank you very much for answering all the questions. It's great to see that we've got so many through. So if you're happy to keep going and others are happy to listen, that'd be fantastic. But please do, you know, if you do need to get on with something else, please feel free to maybe answer them at a later date if that's easier.
No, I mean, I had a meeting that I had canceled, fortunately. So yeah, I have no problem. I can stick around if people are willing to stick around. But you know, if you have to leave and I haven't answered your question, I'm happy to respond to an email. But I'll stick around, you know, and answer ideally all of them.
Cool. Thanks, Bhavik. We'll see how we get on then. Thank you.
Okay. All right. Thank you, Sarah. So yeah, I think I was at Benoit's question, broad question. Okay, could you please comment on how you handle the large amount of uncertainty? Okay, yeah, fine. So I think I just got that. So Benoit, your work is relevant over there. Maybe we need to talk more. Nilay, to what extent do we need to invent new technologies, or do we have all that we need and need better systems engineering? Yeah, that's a great question. I think a lot of the technologies we do have, and we haven't really used them as much as we can. And particularly, we have not looked at those technologies from this view of developing, you know, synergistic solutions. I certainly think there is need for new technologies, no doubt about that. But the need for systems engineering is also very much there, at least as much as that of new technologies. You know, so I would say, and this is a biased opinion, is that I think the systems engineering part, you know, to develop these synergies between technological and ecological systems, that need, I would argue, is greater at this point than getting purely new technologies. Because we have neglected this connection with nature for way too long, at least 200 years. So I think that connection, you know, the more we understand it, the more it will motivate, you know, further innovations on the technological, but also the ecological front. Okay, so then moving on with reference to the diagram of vegetation absorbing SO2 in the US, is that SO2 emitted by the county itself or the average SO2 emission of the US? No, this is SO2 emitted by the county itself. So we consider the SO2 emissions from each county and the vegetation that is actually there in each county, you know, using the National Land Cover Database. And we used iTree to quantify the capacity of the vegetation to take up SO2. So that's how we did the comparison and got the map that I showed earlier. How is cost to society calculated, and is it reliable? Okay. The cost to society, we are using a model developed by the US EPA called BenMap. And essentially what that is doing is it is considering the different emissions. You know, we are only considering criteria air pollutants over here. So it is considering the health impact of these emissions, and those values have then been monetized using, you know, work by environmental economists. Is it reliable? Well, you know, it's as reliable as any economic type of calculation. You know, this type of calculation in environmental economics is quite old. People have been doing this kind of calculation since about the mid-80s. So there's a lot of data, a lot of literature, and these sorts of numbers are very widely used. This is a standard EPA model that is used in the US for policy making and things like that. Okay, so moving on, talked about LCA and other global approaches to tackle the world's issues. Coming back to a smaller scale, do you think we should focus more research work in understanding nature processes and how to scale it up? Yeah, for sure. We do need to understand nature's processes and how to scale it up. One thing I will say over there is that the way we should approach this, it should not be in the way of traditional engineering. If we wanted to scale up, for example, vegetation for, say, carbon sequestration, a purely technocentric approach may be the development of genetically modified trees that can take up more CO2. Such trees do exist, and maybe they do have a place in the grand scheme of things. But the benefit from a sustainability point of view of those types of solutions are not likely to be as high as of a more indigenous and native type of vegetation. So what we are doing is trying very much to stick with natural ecosystems, indigenous species, and not try to do too much tinkering with nature. Because we don't just want a unidimensional type of approach. We don't just want to take up CO2. We want to provide ecosystem services. And that's very wide. So biodiversity is also important. I mean, loss of biodiversity is a root cause for the current pandemic. So understanding nature's processes certainly is important. Scaling it up is also certainly important, but I would really focus on looking at how ecologists have understood this and how can we, do this in an ecologically appropriate manner. Okay, how can engineers influence positively public perception on new technologies? Yeah, I mean, I'm sitting in the US here, and the politically speaking, this is not a very science-friendly environment right now. I think the way to influence public perception on new technologies, but also on many of the problems, the environmental challenges that we face, is maybe we should not think purely like engineers, where we try to provide, a science-based solution and provide a rational type of an argument. Somehow that doesn't seem to have worked very well so far. I was reading a book, I just finished reading it, that talks about some of these kinds of issues. The book is called I'm Right and You Are an Idiot. Okay, very, very provocative title. But it's talking about, how the social dialogue has become very polarized, and that has made it very difficult for people who are actually so-called experts, including, I guess, us engineers and others, it has made it very difficult to positively influence public perception and so on. And the traditional sort of, scientifically based and rational arguments and things don't seem to work. So that book does get into some of the other ways, that may be more effective. I think, education is critical. That's one thing that we can do, if you are in a university. But I honestly, I don't have a clear answer to that. If you know the answer, please let me know. I'd love to know. What are the levers considered in the cost for society reduced by the environment? In this case, okay, in this case for the chlorine factory, right? Yeah, so in the cost for society, as I mentioned, we are using BenMap. So we are only looking at criteria air pollutants in that particular example. Primarily, the biggest contributor is NOx emissions, nitrogen oxide emissions, because of the problem of ground level ozone formation. This site is not very far from Houston, and so it's very populated, obviously, and that is the cost that is contributing the most to our social cost calculations. Okay. Okay, second question from Peter. It seems fine. That's great. In trying to implement technological ecology solution, what risk to human health are we facing owing to that we will potentially have more interaction with our ecosystem, and bearing in mind the current problem? Great question. Right. So, yeah, this is something that I haven't really thought very deeply about, but this thought did occur to me because I was reading that, in the northeastern part of the United States, a lot of the land here used to be farmland. And after about 1930, 1940, it gradually, farming became less and the region became more and more forested. What has happened is one of these zoonotic diseases has actually become quite much more common in the northeastern part of the United States, and that is Lyme disease. So ecological restoration, the way it happened, has actually encouraged and increased the prevalence of Lyme disease. Lyme disease jumps from deer through ticks. It jumps to people in that way, okay? So, but I mean, why has Lyme disease become so prevalent? The problem is that the forests, the trees came back, but biodiversity did not. The predators were not allowed to come back. And because of that, there is a huge overpopulation of deer. There are lots of collisions with deer, which is another problem. So, this is something I think we know enough about these things, and that is also one of the reasons why I've been talking about ecosystem restoration and not of a single species or of a monoculture or of some genetically modified trees or something like that. The restoration needs to happen with biodiversity being given a lot of importance, because otherwise you're right, maybe we'll just end up creating another COVID-19 kind of a situation, which would be unintended harm and highly unfortunate. So great question. I need to think more about this. In the analysis of the private versus public cost, how do you transfer health and environmental impact into monetary values, right, as cost to the public health system? Yeah, so this is similar to what I already said, right? Using BenMap, you're using the environmental economists' developed approaches. How can we argue with Bolsonaro, right, about the value of Amazon's cloud services? I presume you mean the Amazon forest, the Amazon jungle, Sandro. Well, yeah. In this book I mentioned, one thing that the book starts out with is saying that if you go as an expert, you're going to go talk to the people who don't trust science and all that, politicians and so on. Talking with them is very different as compared to talking with your students in a class. The students generally tend to trust you. They tend to believe you. So you're going from a position of trust. Talking to people like Bolsonaro or Trump for that matter, the trust doesn't exist. So that conventional way of conversation that we are used to, because we talk with people who seem to trust us, I think do trust us, that's not going to work. We need a different way. I don't know what the right way is here, but clearly, one has to rely more on the heart than the head, it seems, and, politics. Okay, in the cost to company versus cost to society, you say the TES design alters the conventional curve. How do you take into account the land area required, right? And why does the design experience the sudden jump in cost to company that we see? Yeah, so land area. The way we are accounting for, so we've accounted for land area in a couple of ways, okay? Land, we have considered a 20-year time window over here. So one way in which we have accounted for land is we say, well, we need to buy the land, but at the end of the 20-year period, we get a salvage value. And the land essentially, land doesn't lose value, right? If anything, by planting the trees, we will be increasing the value, but we are not taking that into account. So the salvage value of land results in the land area is effectively being canceled out. Okay, so that's one way in which we have done the calculation. The environmental economists that we work with, they did not like that approach, and they have recommended that we take into account a certain small rent that gets paid to the land. That is the way they tend to take land area into account. And so we have done some preliminary calculations with that. The general trend doesn't change much. The numbers do change, but the overall conclusions don't change much for that particular example that I showed you. Why does it experience the sudden jump? I'd have to go back and look at that work more carefully. I think it has to do with the fact that there are some linearizations that we are doing in the model, and we're switching models when we start getting to the large land areas. Because if you noticed in that curve, the jump happens when the land area goes above about 40 square kilometers, okay, and it goes up to 60, 80 square kilometers. So that I think is the reason for that. I'm not 100% sure of this. If you really want to know the answer to that question, please send me an email, and I can provide you with the answer. Okay, technology versus eco solutions. Why not just focus on technology development, since the eco solutions can be expensive and require land? Well, that's what we are showing. Ecological solutions, they will require land area, no doubt, but they actually can be cheaper. That is why we should consider both of them, right? If we just focus on technology development in the way we have been, we end up creating all this unintended harm, right? Finding whales with 25 kilograms on plastics in their stomachs, right? That's not what we want to do, right? So that's why we must explicitly account for the role of ecological systems. How are they supporting and sustaining all of our activities, including the technologies that we develop. Okay. Explain the graph showing circulatory systems resulting in higher global warming. I'm not sure which graph this was. I'm not sure if I understand this question. Maybe you can ask it and I can get to it later. So I'm going to leave this for now. Okay, is there a way of capturing carbon emissions before it is released into the atmosphere? Yeah, there's lots of work going on carbon capture. People have been working on metal organic frameworks, for example, for separating out the carbon. There are chemical looping types of technologies that can, basically get you the benefits of combustion, but give you a pure carbon dioxide stream. So there's lots of work going on in that area. If the CO2 ends up in the atmosphere, then obviously vegetation will play a role over there. There are estimates that if the planet was ecosystems were restored in the land that is available, we would capture 20% of the emissions that are of CO2 emissions on the planet today. But there are lots of technological solutions too that are available for direct air capture purposes. Okay, to what extent will the mindset of circular economy affect our exploration of new solutions, materials, which could bring new and maybe better solutions to our problems? Yeah, it's a good question. I think, currently at least circular economy is hot. Companies are spending a lot of talking time at least on that and are interested, in supporting this type of research, and things like that. So I think it is already affecting the exploration of new solutions and materials. And I think that is only going to increase over time because the problems of, material waste don't go away, right? I mentioned the dead whales with plastics in their stomach. That is, that really gets to people at a very visceral kind of a level. And that results in a societal push towards change. Right. So, that is something where it is happening very much for plastics. And a lot of the companies that make plastics are very concerned about that. That's why we've been able to get some industrial funding even for that work. So I think it is only going to increase and it will result in, I think new materials, better solutions to our problems. Time will tell, but I think the trend is very much in that direction. So high concentration emissions will be cheaper to use technology, but doesn't that mean greater environmental damage? No, not necessarily, because with the high concentration, you're using technology to remove the emissions. You're not allowing the emissions to get into the environment. Okay, so what I'm saying is that, when the concentration is high and you want to remove the emissions, then using technology makes more sense. Okay, it seems. So you use technology, remove the emissions, they don't go in the environment. So there will not be greater environmental damage. Okay. All right. With lockdown in London, we can see the stars and have clean air again. What value can we attach to them to put into our optimizations? Yeah, great question, Sandro. So, I mean, if we were to do a public cost type of calculation, there is a value that economists assign to scenery and to stars, or the ability to see stars and clear views and stuff like that. So there are ways by which we could incorporate the value of the cleaner air and the joy of seeing stars in the sky into the optimization, right? It would get into the public cost type of calculation. Okay. What can be done to help emerging economies not follow paths of countries like in the US with regard to emissions and economic development? And is that fair? Yeah, good question. I think, a lot of emerging economies already have ancient traditions that rely on ecological solutions. Okay, a lot of the inspiration for the work that we started doing on techno-ecological synergy actually came from my spending time in some of the villages in India looking at traditional methods. These traditional methods really respect nature, and they have been developed, to work with nature while respecting its limits. Okay, so I'm talking of ways of irrigating, farmland, for example, of managing groundwater, of cleaning up sewage, these sorts of things. So a lot of emerging economies have a tradition of this, what is called traditional ecological knowledge. Unfortunately, a lot of those things are getting lost and forgotten. And the assumption has been that, Western technology is always better. That attitude, is not a good one to adopt. And there is some effort. I know of a lot of efforts in India that are trying to actually encourage the use of traditional ecological knowledge along with, more modern types of technologies. So I think there is lots of work to be done in this area. The work that I'm familiar with, a lot of it has to do with water and with farming practices. There are farming methods that are being restored in South America. There's a project that I know in Belize, for example, where they're looking at some of the indigenous farming methods and to see if they can be adapted to the modern world that we live in. So that's kind of a partial answer to your question, I think. To what extent do you observe TES design being used in engineering projects with sectors? Yeah, so, okay, so far, the use of this that I have seen is, very little. I told you that we have done some projects with Dow Chemical, Eastman Chemical, American Electric Power, and a few other companies where we have evaluated the ecosystem services that their land could provide to their manufacturing sites. And I was told that Eastman Chemical actually is implementing some of those ideas. The other application that I have seen is the National Renewable Energy Lab has an experimental site where they're developing a techno-ecological synergy for solar farms. So they have solar panels, and the land on which the solar panels are, they're trying to develop ecosystems on that land in a synergistic manner. We're talking with a company in the US to do that type of work. It was supposed to start in May, but with this shutdown, I don't know. I don't think it's going to happen in May now. And then there is work in the urban planning space. A lot of cities, as I mentioned earlier, are adopting green infrastructure types of solutions. So those are some of the applications that I'm aware of. Where these types of ideas are gaining some traction. So TES example, does it include the cost of land? 38 square kilometers is a lot of land. So Sirish, yeah, I just answered that, right? So the cost of land essentially cancels out because of the salvage value, but we are now including a rental value of the land. And I did not show those results because they are very, very preliminary. But the preliminary results are showing that the overall trend is not all that different. The curve shifts a little bit, but not by a lot. The benefits are still very much there. How do you factor the impact of a distributed production process? So distributed production, from a TES point of view, might actually be beneficial, and even from a circular economy point of view, might be beneficial. One thing that we've been wondering is, if we think about a circular economy, is distributed production going to be better than centralized type of production? My suspicion is that it will be, because the economies of scale, there isn't a big benefit. There isn't a large value provided by economies of scale for many of the technologies that we are talking about. When it comes to ecological solutions, nature is distributed. Nature is highly distributed, right? So there, nature has evolved to essentially, provide a distributed production system, right? Each individual leaf is a factory, for that matter. How cheap will renewable energy become in the near future? I think it will continue becoming cheaper. Nobody expected solar photovoltaics to fall as much as they have. It is already competitive, with conventional fossil energy. Keep in mind, one of the reasons fossil energy is relatively cheap is because it is heavily subsidized. The International Monetary Fund had a report come out maybe 3 or 4 years ago that quantified the subsidies that are provided to the fossil industry, and they run into the billions of dollars globally. Okay, so the comparison is not fair, really, when it comes to costs between renewable and non-renewable energy. Secondly, the environmental impact of non-renewable energy, say CO2, we don't account for that in the cost because, we don't pay any money for the CO2 emissions. Certainly not in the US. In Europe, yeah, there is emissions trading and things like that, but still, the full cost is not being included in the price of many of these energy sources. If we include those things, renewable energy, I think, will become even cheaper as compared to non-renewable energy. Cost to company versus cost to society curve. You say TES design alters the conventional curve. How do you take into account the land area? Yeah, so land area is a great question, right? So I've already answered that. Okay, let's move on. Are there ways for energy engineering to be environmentally conscious, but also cost friendly for poorer communities, especially in developing countries? I think there is a win-win opportunity over here. I'll give you an example. I said, that some of this work was inspired by spending time in some of the villages in India. In the state of Rajasthan in India, there is a town called Alwar, and there is an organization, a non-profit organization over there called Tarun Bharat Sangh, which basically means Young India organization. What they have done is they have restored ancient practices for collecting water and replenishing groundwater. Okay, these practices were replaced by dams and canals and so on. And over the last 80 years or so, 7 of the rivers in that region dried up. This is an arid region of the country. So they restored those old practices, and the people, I met the chief scientist of that organization, and he is not even a high school graduate, but he knows the land, he knows the region, he knew those old practices. He spoke with his grandparents and others. And the practices involve building small dams that will collect water in areas that are fissures in the ground, and those fissures allow the water to go quickly into the groundwater. So when it rains, the groundwater gets recharged. The water doesn't just run off that much. And that brought the rivers back. So 7 rivers came back to life. Okay, and this organization has won all kinds of awards, for the work and so on. So I think actually these kinds of approaches are going to be much more cost friendly for poorer communities, especially in developing countries. I don't think that potential has been fully understood or utilized yet. Okay, these are standalone optimizations, or they're competing for resources against parallel investments. Have you considered looking at this as an interagent based competitive problem? No, not yet. I mean, that's sort of the short answer. There are, I mean, we have looked at this from a multi-objective point of view so that we get an idea of the trade-offs that are involved. The kind of approach that I think you are thinking about, we have not really applied that or used that yet. Maybe that is something that you or others, or maybe even we, might explore in the future. Is it more sensible to try and implement solutions to many small parts of everyday engineering and production sites and see smaller net results, or rather focus mostly on the most polluting areas first, see big results? And from there, have a good base to convince the smaller branches of polluters to join in? Yeah, great question. Difficult to answer. Many times, the big polluters and they are likely to be the ones who are most resistant to change. If they are not resistant to change and are willing to try out some of these solutions, go for it, is what I would say. The smaller sites oftentimes are likely to be, more willing. I mean, it really depends, right? If it's a large corporation like a Dow Chemical or a Unilever, they are, big sites, they are probably going to be willing to change and consider these things. And that's probably why all the projects we have done so far have been with these big companies. So, I think the answer is it very much depends. If the big players, if we can focus there, that, there is more value there. But, the small players could be an individual household. If you have a yard, planting a tree, right? Or planting native vegetation. Those are little things that can be done in one house or in a neighborhood or in a city, that could certainly add up. Is it conceivable that regulatory agencies will impose ecological TES conditions before approving new engineering projects? It would have to come from local and central governments. Yeah, Sirish, that's exactly right. In the US right now, it is not conceivable, to put it bluntly. The EPA is in bad shape, and regulations, if anything, are being removed. But there are local governments that are starting to play a role over here. For example, in New York City, there is a requirement to put in green infrastructure in all of the new developments that get carried out. They are required to at least consider green infrastructure. And a lot of green infrastructure for managing water has been implemented in New York City. Unfortunately, some of it, it seems, has been implemented in a manner that is not necessarily scientifically sound. It's sort of become more of a religion almost for some people, and those things are likely to backfire. But there is effort from urban areas and urban municipalities. Another effort that I know of is I believe it's in Lexington, Kentucky. I mean, you wouldn't expect Kentucky to have a very progressive type of a government, but in Lexington, they have a big project with, I believe, the Nature Conservancy, where they are actually considering essentially TES kinds of systems for improving air quality in regions where the poorest people live and where there are severe health problems due to inferior quality of the air. So there are those kinds of things happening at local levels, as far as I know. At a central level in the US, as far as I know, there is nothing as of now. Maybe there are things happening in Canada, maybe in the United Kingdom, other parts of the world that I'm not familiar with. But if there are other activities of this type, that you know of, please share them. I'd love to hear. Why don't aircraft use solar panels for energy like satellites in space? Good question. I don't know, to be honest. I mean, there must be some technical challenges with that. Maybe they're not high enough. I mean, I don't have the expertise to answer this question in any kind of a sensible way and credible way, I think. So that's all I'm going to say over there. Maybe it's a technology that is being developed. I mean, there are these solar powered flights that I've heard of, and I've seen pictures of that, but they're not commercial yet. Okay, I think that is the last question. Okay. So I don't know how many of you are still there, but thank you again for those of you who are still hanging on. I certainly appreciate your interest and input. And as I said, if there's anything further to answer, to discuss, further work to do, I think there's lots of opportunities and challenges and real need. I'm happy to continue the conversation.
Avik, I just want to say thank you very much for a really interesting seminar, and thank you so much for answering all those questions as well. I think you've set a record for how many questions you can answer at the end of a webinar, so I really appreciate it, and I know that everyone from the department does as well. And hopefully we can invite you over once this is all over and things are back to normal,
Sure.
show you around the department. But yeah, thank you again very, very much from all of us.
Okay. Yeah, thank you very much. Appreciate the invitation and the opportunity.
Great. We'll be in touch soon. And right. Just to say to all the attendees, we'll make a recording available as well after the seminar.
Okay. Thank you. Goodbye, everyone.